Hey everybody. So I'm Scott. I'm from Deepgram. We're going to be talking about the past, present, and future of automatic speech recognition. I say automatic because, well, we're talking about machines doing it, not humans. Actually, speech recognition for humans has been around for a very long time, but we're going to talk about machines. And so I'm from Deepgram. What we do is we serve the enterprise and B2B community, and we do speech recognition, customized speech recognition, but we do it in real time, and we do it on not consumer-related audio. So what I mean is, hey, there's command and control like you use for Google Maps and Google Home and things like that. We're talking about like meetings and phone calls, things that are happening in real time with usually lower fidelity as well. So I have a PhD in doing signal processing. So I used to build deep underground dark matter experiments, and so it was all on acoustic waveforms and doing machine learning in order to tell the difference between signal and background in that context. And we took that same technology and applied it to audio. It was sort of you could try to look for particles, but it actually becomes a solved problem once you figure it out. Hey, you just kind of let it go. But in the voice world, it's always changing. And so that was much more interesting to us. And so we started Deepgram to help with that. And actually, if you think about this problem, if you just does anybody know like how many words are just like printed just like on the internet? It's not that many actually. It's around 10 trillion words. But people, there's 7 billion people, and we speak about an hour and a half a day, each of us speaking, and we speak at about 180 words per minute, and that's 6 trillion words just a day that we speak. So speech is super, super natural. It's something that feels really good to us, but it's also just not. Words that are being transferred between people without context, there's a lot of tone, there's pacing. There are these other things that are important in there. And it's this very natural form of communication, but it was very hard to crack with the machine because of the nuances. So now, to talk about the past. So this, you can go back to the 60s where this first started, but when things really started to pick up is in the 80s when people started to apply hidden Markov models and make acoustic models in order to do a task that looks similar to this. So I'll explain the process. So imagine somebody says tomato juice. Actually, how many people are tomato people and how many people are tomato people? Tomato? I'm a tomato person for sure. Tomato? We have a few. Okay, so we have a few. But when you say that to a speech recognition system, you might be a male or female. You might have a lower tone to your voice or a higher tone to your voice. You might say tomato, or you might say tomato. And the speech recognition system has to deal with all of this. But what it's doing is it's taking in the recording, and it's trying, this is, again, sort of the old techniques. It's taking in the recording, and as a first step, it's trying to just guess the phonemes that people are saying. So, and by phonemes, I mean like the alphabet of speech. And so just like there are letters in writing down words, there's 26 of them, well, there's 39 phonemes, like ah, ooh, could, the, like all these different sounds that we make in English. And so that's the first step. It says, hey, I'm listening to this acoustic waveform that's coming in, and then every timestamp I'm trying to guess, is that a T sound or is that something else? And actually, since this is a technical talk, we can go in a little bit more. It's actually a probability distribution function as a function of time. So every timestamp, it's every phoneme it's trying to guess. And this happens like every 40 milliseconds. So it's a lot of data. It's a huge, huge matrix. And then the next step is to try to take that huge matrix and turn it into candidate words. So it doesn't go straight to words right away. So that acoustic model tries to guess phonemes. And then the next step is either a hidden Markov model or a weighted finite state transducer, which tries to take all of the candidate phonemes and then guess words as a function of time. So now you're going from like every 40 milliseconds, 40 possibilities, to every 40 milliseconds, 100,000 possibilities, because there's a lot of words in the English language. And this is a really bad like combinatorial problem. If it starts to get really computationally intractable. It takes up way too much memory and too much computational power, and so you have to take shortcuts all over the place in order to make it work at all. And this is where the next step comes in, where there's a language model, a text-based language model, so it's not an acoustic-based language model. So it just learns from like books and things like that. And then there's a beam search, which is literally just it's just cutting off. So it's saying, hey, I'm only going to take like the top 50 words, and I'm going to cut everything off at every timestamp. And so that's how it goes along. And this is how speech recognition worked from the 80s until like 8 years ago, essentially. It was all just like this. And people made incremental gains, but there weren't any big boosts for a while. And so this is the kind of technology that you saw, like, or you see still actually in like Nuance's Dragon product. So did anybody ever buy that? Like go to the store and get the box with the headset? Yeah, I remember I did. I thought it was so awesome. You know, like I'm gonna go train this. It's gonna be great. I'm never gonna type again. Well, we're still typing, right? So one of the reasons for that is like, hey, a natural speech interface isn't just the killer interface for literally everything. It makes noise. You know, that's part of the problem. But also, if you need it to be super precise and organize things, well, it's better to be using a keyboard or a mouse in a lot of ways. But still, this is actually really useful in some circumstances. So like legal depositions or medical transcription, there will be people that they'll buy this product and they'll do it as an enterprise, and they'll do what's called re-speaking or voice typing. I don't know if anybody's ever heard of this, but the first time I heard of it was like crazy. But essentially, somebody's listening with headphones, and then they have a microphone, and they're speaking what they're hearing. And the reason for doing this is to increase the signal-to-noise ratio. And so what they're doing is talking like a robot, basically. And so they're transforming the input as a human, transforming the input in real time into something that's easier read by the machine. And this is still used, and this is still how like a lot of medical transcription is done today. But actually, there are companies now that are replacing this with much better techniques that aren't based on that, because actually you can cut out that step if your models are good enough. So to give you an idea of what the architecture looks like, I mean, we don't have to go through the whole thing here, but essentially it's complicated, and you have that acoustic step, and then you have to prune and do your memory management and all of these things, and each one of them is a different piece of code. It's not one big thing. Each one is kind of a module, and if you change anything in a module, then you have to change all the other modules, and essentially it's all very much academic type code too, and so it's very hard to change one thing and not break something else. And so people get very scared once something is working, like, whoa, 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 don't touch anything, it's working, you know, et cetera. So, but you can find versions of this type of code, this hidden Markov model type stuff out there in the world, like CMU Sphinx has an open source version, Caldi has an open source version. So if you want to get your hands dirty, you can go look at how all of it works. It's very complicated though. So now the way the world works is there's at least a blend of deep neural networks or full deep neural networks. And so the blend is like Google and Amazon. They sort of modernized that old way to do it, and they put in deep neural networks in certain spots. They don't do the whole thing, but in the acoustic model, they do. And this is what you see like with Amazon Alexa and Google Home. But what they do is consumer-based command and control, okay? So what do I mean by that? I mean, if you say, OK, Google, that's what's called a wake word. Okay, that's not really speech recognition. That's looking for, you're listening across all of time, and you're only looking for like a vocabulary word of one or two. But when it goes, it fires off, and you say, oh, OK, now I'm going to start recording, and then I'm going to record this command step. Okay, and so like, OK, Google, start my morning playlist. Like, hey, I want to listen to some music, right? And then if it understands it, it'll trigger an action. And so this is the control side. So OK, Google, play me some music. It starts playing some music. Everybody's happy. That's good. Maybe you're doing it on your phone. Maybe you're doing it with your Google Home. You're doing it in a controlled environment. And you're doing it with a lot of bandwidth, because actually for this type of task, they don't compress anything so that you get the most fidelity and so that the speech recognition works well. But if you do this on conversational audio, or you do it in real time, right? You have meetings, you have phone calls, and now you have to shrink it down with an Opus codec and all these other things that you have to do in order to actually make all of these APIs work together. You can't just stream out linear PCM data, it's just way too large. Then you start to run into these problems where it's not going to have as good speech recognition because, hey, the domain is limited to this consumer vocabulary that's over here, but we're talking about APIs, and we're talking about all these other vocabulary words that it's not going to recognize, but also we're in this acoustic environment with compressed audio that it just doesn't jibe with. And so, like I said, the brittle stuff is hard to correct, so you just leave it and you just hope for the best, essentially. But this is This is where real problems come in, lots of accuracy loss. Maybe it's accents, maybe it's crosstalk, maybe it's whatever, but you can't adjust and the system actually can't get better. And so what is the future then? What is actually going to happen and make this all very good? And I think the prediction should be that this will be all very good soon. Hardware is getting a lot better. People are getting a lot more organized about how they're attacking the problem, et cetera. But hey, maybe you start out at 71% now, but if you use end-to-end deep neural networks and you do training and you allow online training and active learning throughout time, then the models will just get better over time. And so it's no longer the brittle, old, strapped together stuff with shoestring and bubblegum. It's one monolithic model that's end-to-end deep learning, and it's based on just data-driven approaches. And what I mean by that is you have an example of audio. So this is audio on the x-axis here. It's actually time. So on the left is the past. On the right is the future, or it's going off to the right. And it's only 3 words that are being spoken. Of course, if you have a long conversation, this gets really, really long. Going up is frequency, and down is also frequency, but it's lower frequency down, higher frequency up. And you can see 3 words here. So it's Uber, driver, partners, okay? And if you were to send this exact recording to the old style systems like Google, they're prone to make mistakes. Like this actual literal recording, it's Hebrew driving partner is what it comes back with. If you allow the model to be trained, then it can make that mistake far fewer times and actually get it correct. It doesn't matter if it's female, male, lots of noise in the background, et cetera, it can adjust. But to give you something fun here, so essentially like look at the partners here. Do you see in the upper right-hand corner, there's like a big splotch? This is high frequency, and it's all the way to the right. This is the S sound. It's like high sibilance and very dispersed in frequency space. These bands that you see moving up and down are like a person's voice going up and down, but there are harmonics all over the place. And so this is what gives a person a unique timbre to their voice. But essentially the shape of that, whether it's going up or down, the pattern that it works out in, is it high frequency or low frequency? The model is looking at all of those things, and it's essentially doing facial recognition plus some other stuff on it, looking for words, not faces though. So the way that training works is you feed audio into the system, and then portions of it will be fed to humans that actually look at the output of the ASR. So automatic speech recognition comes out, humans look at it and they say like, ooh, that word's wrong, this word's wrong, we need to change those. But then you change it. So for instance, you're in a meeting, someone says, hey, he'll dial in and share action items about the API. Like a consumer speech recognition API isn't going to do so well on a lot of those words, and also the acoustic environment. But now if the model messes up, a person can go in and say, oop, that was wrong, that was wrong, that was wrong, and then feed that back into the system. And then on the left here, we have training as a function of time. And actually, this isn't accuracy that's being shown, it's error as a function of time. And so this is how a lot of machine learning and deep learning works, where you show it examples, and then it learns just a little bit and gets just a little bit better as a function of time, and the error keeps going down. And so this is how you can go from like 70 to 90+% accuracy on like really crappy audio, even like MP3s that have really, really low bit rate, because over time it can learn all the nuances of the audio and get really good at it. So now, like, we talked a little bit about the future, but where's the future really, really going? So transcription is actually really cool, and transcription is like the first step. Like, what words did people say? But there are more steps, like who said the words? You know, if there are 2 people talking, okay, these words were said, who said them? So this is called speaker diarization, or speaker recognition. But also you can tell, just like, really what you have to do is think like, what can a human do? Human can jump into a conversation and say like, ooh, I think they're talking about this topic, and this person said that at this time. And actually there are a few words that I didn't understand, so I can say the confidence is pretty low on those from my own understanding. This is what the speech recognition is starting to be able to do. It can tell you the words, it can tell you the times, it can tell you the confidence that it has about the words, it can tell you who's saying them, it can tell you how old it thinks they are, you know, what age do they think they are, what name if they're in a database. And then something that's actually really cool is how are they feeling? Are they pissed off? Are they happy? You know, how is the call going? Is the pacing nice? And so this is really important, like especially on the sales side, when you have a lot of people doing calls, or also on the meeting side, if you weren't in a meeting, what were people talking about? What was the topic about? Were you included in it? Was it just a boring old meeting again, or were people having a good heated debate? This is all coming in the future, and it's going to be based on that end-to-end deep learning approach. And you'll start to see like prices drop and everything start to get a lot better, like in the next 3 to 5 years. So that's the past, present, and future. I think we have just a little bit of time for questions, but thank you.
Thank you, Scott.